So, I had stopped last time at a point where I just described how the grating will be able to decompose a beam of non-monochromatic light into spectral orders. Okay. So, a little bit more of understanding of the grating is required, and that is what I plan to do. So, we saw that the grating is able to create a spectrum, basically separate out all the wavelengths that is there in a beam. Okay. And here if you see in this picture, I have just you have seen it last time also. This is what a grating pattern will look like. Okay. Well, once the beam has hit the grating, and then this is what you are seeing on a screen there. So, this is in case n is low. N, if you remember, was the number of grooves on the grating, and here also n is high. If you see the number of n is again the number of grooves that you see here. So, the difference between these two, you can see this pulse or this wavelength is sort of broader. Okay. So, it has a width, a certain amount of width, while this one is very narrow. Okay, here and looks better resolved. Of course, this does not look that well resolved, this looks more better resolved. So, that means if n is high, that means the number of grooves that the beam is hitting is high, then you get better resolved spectrum or better resolution of each of those wavelengths that are separated out. Okay. So, so let me start at this point. Here this was the intensity depending on phi was given by this here, sin alpha minus sin beta. Alpha was the angle of incidence and beta was the angle of diffraction. Okay. So, this is phi. So, the intensity at some particular phi, okay, depending on the integer m, is given by I 0 sin square n phi by 2 sin square phi by 2. So, this is what the intensity will look like. So, let us see how this intensity, this is also an intensity profile. See, this is phi and this side the y axis is the intensity. So, I phi has this kind of an intensity profile. So, let us see how it has this kind of an intensity profile. One is of course, with different m, m is an integer 1, 2, 3, 4, 5, this it breaks up into this. But why is it peaked so much at these points? At certain phi's it is peaked, while the others, okay, it is a small sort of a small patterns here. Okay, that is what we will try to see today. So, if I go to the next slide, let me just explain. Okay, here what I see is the function I phi has a maximum each of height n square. Okay. So, I have to tell you how it becomes n square at all points where the denominator sin square phi by 2 nearly vanishes, when phi by 2 is equal to phi or our multiplication by pi. Okay. So, what I am just saying here is that I phi is of the form sin square phi by 2 n phi by 2 something, yes, upon sin square phi by 2. Okay. If you just see the previous. So, I have just written it is sin square n phi by 2 upon sin square phi by 2. So, when the denominator, that means sin square phi by 2 becomes 0, you cannot have I going to infinity. So, in that case you have to use the limit, you have seen this before also. You have to use the case where it is of the form sine square x upon x square, where x tends to 0, okay, this becomes 1. Okay. So, now if sine square phi by 2 is 0 here, this is 0, we can approximate it to it is very small, sine square phi by 2 is very small. So, you can say sine square phi by 2 is equal to phi by 2. Okay. So, you can write this whole equation in this form. Okay. And once you write it in that form, sine square n phi by 2 upon phi by 2. Okay. So, I want this the denominator and this numerator, this part to be the same. Okay. So, if I multiply by n, and I do it before taking the sine square, n divide by n, sorry, and I multiply also by n, okay, and then I take the square. So, this becomes n square. So, so my intensity I is proportional to some undulating factor here because of the sign, and then is proportional to n square. So, you have come across this kind of understanding even during when we were studying second harmonic generation, where you get a peak of second harmonic generation. So, here again it is a similar kind of a equation, and that is how you see. That is why the function I phi has a maximum height of n square at all points where the denominator sine square phi by 2 nearly vanishes when phi by 2 is 0 or multiple of pi. Okay. So, if it is 0, it will become 0. If it is multiple of pi, also sine of pi, multiple of pi becomes 0. Okay. So, so here what I mean by this n is high, okay, that means n is a large number. So, this intensity, this height of this intensity will become n square. So, if you take n is equal to 10, just as an example, n is equal to 10, your height will be proportional to 10 into 10, 10 square. Okay. So, that will be 100. But if n is low, suppose n is 5, n square will be how much? 5 square, that is 25. So, this height will be only 25, while this height will become 100. And automatically when the height becomes 100, it will become a very narrow pulse. And there itself, the sharpness of the pulse comes into the picture. And why do we need sharp pulses? Sharp pulses means the resolution is very good. We will come to the resolution part, but this is what you see. So, if n is large, then this the height of this intensity also becomes large, and it is easier to detect, easier to separate out all the wavelengths. So, all these wavelengths will be sharp, absolutely sharp, sharp featured lines which you can detect. Okay. So, that is the advantage of n, okay. And all we have done is derived it from this equation, okay. And that is when sine square phi by 2 tends to 0, that is what happens when it. So, when sine square phi by 2 becomes 0, these are at these points 0, 2 pi on this side, if I call this the central. So, phi takes these kind of values, see here phi takes these kind of values. So, m is equal to 1, it will become plus 2 pi, m is equal to 2, it will become 4 pi. So, at 4 pi again you will get a peak, on this side minus 4 pi again you will get a peak. So, that is what it says, at these points of phi, values of phi, you get very high intensity, okay. Because here I have just written m is an integer and is called the order of the diffraction pattern, that I have told you even last time, m is the order of the diffraction pattern. So, depending on the order of the diffraction pattern, you at those points you are going to get very sharp, sharp lines, sharp and high intensity lines. The others are say they are all tiny, 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 tiny lines like this, all these tiny, 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 tiny peaks. Okay. So, between the principal maxima, there are weak secondary maxima. The first secondary maxima being only a few percent of all the principal maxima when n is large. The maxima are separated by points of 0 intensity. Okay. So, if I go back to that again, these are the principal maxima, and all in between you have small, 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 small maxima. Okay. How are they separated out? Means what is the value of phi in which these small, small maxima occur? That's what I am trying to say. So, that happens when n phi by 2 is equal to q pi. You can see it from that equation. Okay. Okay. So, these points of maxima are separated by points of 0 intensity. Again, if I go back, you see here. So, sine square n phi by 2 will become 0 when n phi by 2 is 0 or multiples of that. That is what exactly I am trying to say here. N phi by 2 is equal to q pi, where q is an integer 1, 2, 3, 4 like that it will go in. So, that means half, substituting for phi, half n 2 pi by lambda d sine alpha minus sine beta, this is the diffraction angle and incident angle on the grating, is equal to q pi. Okay. So, d sine alpha minus sine beta is equal to q lambda by n. Okay. So, q by n is not an integer, though q is an integer, n also is an integer, is a large number of lines that the beam covers. Okay, that is also large. So, q and n being integers, okay, though q and n are integer, q by n should not be an integer, then this equation does not work. Okay. So, this does not have to be an integer. So, in these points you will get 0 maxima. So, these are the points, these points, these points, these points, these points, these are where you get this 0 maxima, where it becomes 0, and between the two zeros there is one maxima. Okay. So, that is at those points you are going to get that. Now, at this stage I think I should tell you what is the resolution of a grating. Resolution means, suppose I have two lines or two wavelengths and they are very close to each other, but really with using the grating I want to separate them out. So, how do I know? Mathematically, how do I put it? How do I quantify it? Okay. So, suppose I have these two lines. Okay. This a green, I have just shown it in green, it need not be green and yellow line in the wavelength. This is the wavelength, and this is of course the intensity of each of these wavelengths. Okay. So, this is one wavelength shown by green, this is the next wavelength shown in yellow, and these two are very close to each other. Suppose they come very, very close to each other, you are not going to, you won't be able to distinguish them. When do you begin to distinguish these two lines? When you can see the peaks here and the peak here, you can see one peak here and one peak here. Then you will see two distinct lines which are close to each other. You know, if you see it on a screen or something, there are these two lines. So, if they are very close, I am unable to distinguish, but when they are like this, I am able to distinguish. So, I want to find a condition under which these two lines are distinguishable. Okay. So, here suppose I take the peak of this line at lambda 0 say. Now, this one occurs at lambda 0 plus half of lambda 0, that means this distance, lambda is increasing in this direction. So, this is lambda 0 is the central part. Lambda 0 plus this half, at this point the minimum of this coincides with the sort of the maximum of this coincides with the minimum of the next line. When that happens, then you can see more or less two lines. So, by the dashed line I have just shown, if you observe two spectral lines like this, then you can say that they are resolved. Okay? That is the whole idea. So, here I say consider the case when two components of the wavelengths are of equal intensity, and to fix a displacement of maxima at which the components may be just resolved. Okay. If these two lines go even further apart, well and good, it is nice for you, it is very well resolved, but always that may not be the case. So, when do I say it is just resolved? This happens when the intensity maxima of one coincides with the minima of the other, and it is the same as saying lambda 0 plus minus half delta lambda 0. Delta lambda 0 is this part, this half part. Okay. Are wavelengths of two components. The quantity delta 0 upon delta lambda 0, lambda 0 upon delta lambda 0 is called the resolving power. So, this quantity will give you the resolving power. Okay. Pictorially I know when they have got just resolved, when these two are just separate. But suppose I want to quantify it, then I have to give a quantity of lambda 0 upon delta lambda 0. Okay, delta lambda 0 is this much, this half bit here, from here to here, here to here. Okay. So, I have to find out how lambda 0 upon delta lambda 0 can be, can we find a formula for that? Okay. So, let us see if we can find a formula for that. Now, suppose I write P is equal to sin alpha minus sin beta. This is the same thing, I am just putting it in terms of P, sin alpha minus sin beta. Alpha of course remains the incident angle and beta is the diffraction angle. Then dP is equal to q lambda by n. Okay. Okay. So, P actually, see this is the P, this is q lambda by dn, that comes from the previous equations. Okay, you can derive it from one of these equations. See, I am calling this P. So, dP q and lambda, q lambda by n, here, d sin alpha minus sin beta, which I have derived from here. I am just calling this factor P just to make life a bit more easy. Okay, and q lambda by n, exactly this formula. So, here, so P is q lambda d by n. Okay. Now, suppose q takes values 1, 2, 3, 4. So, I put q as 1, then say P1 is equal to lambda by dn, and P2 is equal to 2, suppose I put q as 2 lambda by dn, and delta P I mean P1 minus P2 minus P1. P2 minus P1 I am calling it delta. That small change in P is given by lambda upon dn. This minus this will give you lambda upon dn. So, now if the wavelength is changed by an amount delta lambda 0, as we saw in the previous picture, okay. Okay, here. So, this is lambda 0. If I add another delta lambda, then I will come to this point, which is of course another wavelength. Okay, that is what I mean. So, is changed by an amount delta lambda 0, then the mth order maxima will be displaced by an amount delta p. Now, this is one delta p, you know. Now from another formula, suppose I do it, I'll do it from here. Suppose from here, somewhere here, this d sin alpha, from this formula, I want to find out, so I want to bring in this factor m, the order. So I use this formula. So this is again dp upon m lambda. Okay. So I am using two formulae. One is this, which are both derived in different times, for which is this, and the next one is the previous formula. From that, what I get is, I get dp dash, just like I got delta p, I can write delta p dash is equal to m by d into delta lambda. So in place of lambda, I put delta lambda 0, lambda 0 plus delta lambda 0, and in the next p I put only lambda 0, and minus the 2, and I will get this. Okay. So when the maximum of one wavelength coincides with the minimum of the other, when does that happen? When delta p is equal to delta p dash. Okay, just think about it. Obviously, that's what I told you pictorially in that graph, and now I am just writing it down in a few mathematical terms. Okay. So delta p is equal to delta p dash. Now just substitute for delta p and delta p dash here. You will get lambda upon delta lambda is equal to m into n. Okay. So I have a nice little formula for my resolution. So not only do I want to separate out each of these wavelengths with the use of a grating, but I want the lines to be very sharp, and I want all the wavelengths to be well resolved, so that I know exactly, which, then only I can do my tuning very well. Okay. So if they are not well resolved, I tune it to a certain wavelength, but actually I think there is only one wavelength there, but really there may be 2 or 3 wavelengths. Okay. And it will just destroy the rest of my experiment. Okay. So for tunable lasers, or for tunable light that you want for your subsequent experiments, you must know what is the resolution, and you must know which order of the grating you are using. Okay. So these two things you must know. So here, I mean, you see, this resolution depends on m, that means the order, and also it depends on the number of grooves. Okay. Order m and the number of grooves. So if I keep on increasing this number m into n, my resolution becomes better and better. Okay. So that means the higher the order in case of a grating, you have a better resolution, and higher the number of grooves that the beam hits. Okay. So suppose this is my grating, and I have a lot of grooves here. By the way, I want you to distinguish between what I had said before, that sometimes you give the specification of the grating as number of lines per mm, or number of lines per inch. Here I do not mean number of lines per inch. N does not mean number of lines per inch or number of lines per mm. It is not the density. Okay, it is not the density, it is just the total number of lines. So I want the beam to kind of hit like this. Suppose the beam is coming here, and it should cover, the beam should cover as many lines as possible. If it covers a whole lot of lines, your resolution becomes very good. So that is why if you just recollect the design of a, a dye laser. Here I had See, this was the grazing incidence, it is called. This is the grating and this is the beam that is coming here. If I keep it at that grazing incidence grating, grazing incidence means the light is just grazing the grating lines. You can see geometrically also, you can see that the number of lines covered by the beam is quite large. If it falls directly at perpendicular, then obviously the number of grooves covered by the laser beam is not very large. So, though in case of a dye laser here, though in case of grazing incidence, the efficiency becomes a bit low. Efficiency means there is a lot of loss of intensity or loss of energy, but then you are gaining in terms of the resolution. So, when we talk about tunable lasers that we are looking for a good resolution. Okay. That is one of the very important parameters. Okay. So, that is why you had this grazing incidence. So, the dye lasers, the resonator is made with a grazing incidence grating, okay, in order to better the resolution that comes in. Here I had written somewhere, I think, maybe you will find it yourself at some time. So, this is the idea of a grating. By the way, I want to tell you, gratings are not just used in a laser cavity. Gratings are used in monochromators or spectrometers. Spectrometers will always have a grating, something that disperses the light and separates out the wavelength. So, spectrometers, that means you want to know in a beam of light what kind of wavelengths are there. So, you use a spectrometer and the spectrometer gives you the numbers of which laser lines are available or which wavelengths are available. So, all spectrometers will have a grating inside it. Okay. And then there are other detectors which detects those wavelengths, that is a different story. But a spectrometer is incomplete without a grating. And the same equations apply even for spectrometers. Same equations of the grating, they all apply for these gratings inside the spectrometer. You have to decide what kind of resolution you need. You have to decide what kind of separation between the wavelengths you require, depending on your use. Okay. So, here I end my discussion on grating, which is a very, very important component specifically for tunable lasers and specifically for applications where tunability is required.